Hello and welcome once again for another ES340 video. This is ES340 day 15 part A, and I believe this will just be a single video in this case. So this is for control volumes at steady state, and we're still talking about entropy rate balance. And I sort of took liberties last time with the problems and such, assuming that you could kind of jump to the conclusion about what happens at steady state, right? Because recall at steady state, all properties are constant in time. And since entropy is a property, of course, that implies that ds dt has to be equal to 0. Okay, since it's constant in time, if you take the derivative with respect to time, the derivative is 0, which makes sense. And obviously the mass flow rates that we dealt with before, that still applies, right? The sum over I of mi dot has to be equal to the sum over E of me dot. Now we mostly, for the most part in this course, we deal with single inlet, single exit, sometimes maybe only single inlet or only single exit, but most of the time we will be dealing with single inlet, single exit, right? Turbines, things of this nature, which means that mi dot is equal, because there's only one inlet, is equal to me dot. But you have to be careful if there's multiple, because you have to actually sum them up. So if you have, say, two inlets, say, I'll label 1 and 2, and one exit, say number 3, then m1 dot plus m2 dot, right, because I'm labeling them 1 and 2, mine is equal to m3 dot. That would be the case in that scenario, right, with two inlets and one exit or something like that. So just keep that in mind when we're dealing with multiple inlets or exits. But that's a rare case. We won't deal with that mostly at steady state. I should specify that. And most of the problems we deal with will be at steady state, and so you can just sort of assume that what you're going to see is mostly steady state problems. Very rarely we'll deal with transient problems. Just be aware that they exist, and occasionally you might get one thrown your way in a homework problem or something. Okay, so at steady state then, what does that mean? Well, we already know, recall the energy rate balance, which is always good. And we're going to go through a similar formulation for the entropy rate balance. And a lot of times this obviously simplifies if it's just a single inlet and a single exit, right? It just becomes let's call the inlet 1 and the exit 2, it becomes m1 dot times h1 plus v1 squared over 2 plus gz1 minus m2 dot, and at steady state that would obviously be m1 dot and m2 dot would have to be equal to each other if it's single inlet, single exit. H2, so minus H2 minus v2 squared over 2 minus gz2, right? That would be something that it would look like. And the similar thing happens with the steady state form of the entropy rate balance equation. Now, when we're dealing with these when we're dealing with the entropy, we're going to typically want to include the energy rate balance. So we practice a bunch of those energy rate balance equations. Don't drop that out of your analysis. You should be thinking immediately, I can use the energy rate balance equation to my advantage. Now, so I would suggest always at least writing it down. You may, in certain circumstances, find you don't need it, but it's always good to have it there. And most of the time you will need it. Now this is the entropy rate. Rate balance at steady state. Because this energy, by the way, this energy rate balance equation typically will help you find a second property or something along those lines. So 0 equal to the sum over j, qj dot over tj, plus the sum over j. Actually, this is sum over I, excuse me, of mi dot si minus the sum over e of me dot se plus sigma dot. Okay, that's my entropy rate balance at steady state. And obviously, if we can have it written for single inlet, single exit for the special case. Remember that this means 0 equal to q dot minus w dot plus m, we'll call the inlet 1 and we'll call the exit 2, why not? M1 dot at steady state. M1 dot, because M1 dot in that case has to be equal to M2 dot, right? That's the single inlet, single exit case. So I would get something like H1 minus H2 plus V1 squared over 2 minus V2 squared over 2 plus gz1 minus z2. That's my energy rate balance equation, and my entropy rate balance zero would be equal to the sum over j of qj dot over tj. And by the way, these are all of the, this is just the sum over all of the heats that are entering or exiting, right? So I might have just a single, it might not even need to be a sum, right? It might be just a single heat, which is often a case that we get. You might get two heats, one entering, one exiting. You might get two heats entering, two heats exiting. You might get 3 heats, you know, and all of that kind of thing, where you would sum up over all those. That's what this equation is saying. However many heat flows we have, plus m1 dot, in this case, S1 minus S2. If it was a single inlet, single exit, right? That's going to be our common equation that we'll see. Won't always be the case, but this is what we could get. Okay. Let me just move this down a little bit. So at steady state then, what does this become? Well, we can rewrite this in terms of S1 minus S2. Or probably easier if we just write it in terms of S2 minus S1. So if I move this over, I get M1 dot S2 minus S1 equal to the sum over J of Qj dot over Tj plus, I forgot my plus sigma dot here. Plus sigma dot, which means just that S2 minus S1 is equal to the sum over J of Q dot J over J Tj times M1 dot plus sigma dot over M1 dot. Okay, so that would be single inlet, single exit scenario. Obviously, if there's no heat transfer, I can eliminate that term. If it's internally, if there's no heat transfer, I can eliminate that term. If there's no if it's internally reversible, I can eliminate the blue term there. I'll just highlight them like this. Oops. So no heat transfer, I can get rid of the red term. No internally reversible, I can get rid of the blue term, right? Okay. Now, isentropic processes. So we've actually seen a number of processes that where we hold something constant, right? So we have the isothermal type of process where the temperature doesn't change, so that's held constant. There's isobaric processes where the pressure is held constant, and things like that. So isentropic processes then are where the entropy is held constant. So that means S2 minus S1 is equal to 0, basically, in an isentropic process. So if I'm at steady state, of course, then my equation then reduces to 0 equal to the sum over J of Qj dot over Tj M1 dot, I'll do the single inlet, single exit example. Just to make this easier, plus sigma dot over M1 dot, right? That would be an example, an isentropic process. Okay, and we can actually look at this on the TS curve. That's one of the curves that we like to look at. You know, it looks something like this. And you can imagine I have, say, a state I'm going to go straight up. S3, S2, S1, this is an isentropic process, right? I could have 3 states, and you notice that I can move in and out of different phases, right? This is a mixture. S3 is a mixture, S2 is a mixture, S1 is probably, because this point up here would be the critical point. I'll highlight it in red. That would be the critical point. So this point up here is probably or is a superheated in a superheated state, right? So we have two of them in the mixture and one in a superheated state, something like that. And it would be similar on the molar diagram, which is the enthalpy versus S, right? You have this curve that looks something like this, similar idea. So if I'm constant, again, I'm going to go straight up through here, similar kind of idea on the diagram. Okay, so you might be, we're interested in processes that are isentropic. So if it's an ideal gas, what does that mean? Well, we know that we had an equation for the ideal gas. Remember, S2 minus S1. We saw this last time. S circle of T2 minus, or maybe 2 times ago, I don't remember, minus R times the natural log of P2 over P1. This is ideal gas. And obviously, in this case, we're reading these values are table values, right, for the ideal gas. Because in this case, we're not making any assumptions. So if we don't make any assumptions, then we can say then we can just read these values off the table because they approximate that integral that we had in that place. Okay, so if it's isentropic, though, S2 minus S1 is 0, so we have 0 equal to S circle of T2 minus S circle of T1 minus R times the natural log of P2 divided by P1. And what does that mean? Well, we can solve this in terms of pressure. For example, we want to know a new pressure. By the way, you also can have an equation with the plus R times the natural log of V2 over V1, the specific volumes there. So the process is identical with the exception of the fact that we have a minus sign there. So you have to be very careful when you do the inversion that I'm going to do now. But let's go about this now. So what does this imply? This means that R times the natural log of P2 over P1 is equal to S circle of T2 minus S circle of T1. Again, this is isentropic. Because I set that equal to 0. What does that mean? Well, that means that the natural log of P2 over P1 is equal to S circle of T2 minus S circle of T1 over R. If I exponentiate, I get P2 over P1 is equal to E taken to the power of S circle of T2 minus S circle of T1 over R. And then finally, P2, the final state, is equal to P1, or you could rearrange depending on what you're trying to find, of course, P1e to the S circle of T2 minus S circle of T1 over R. Okay, so this is my new form of this equation. So if I wanted to find the new pressure, this is how I would go about it. So pressure is obviously exponentially related. The second pressure is exponentially related to the first pressure if it is an ideal gas, right? If we're dealing with an ideal gas. This is in an isentropic process. Which is kind of a cool relationship. Okay, so let's assume that it was not, I'm going to have our first clicker question here. Let's assume that it was not a constant, it's not isentropic, so entropy is not constant, but that S2 minus S1 is equal to C, where C is not equal to 0. Then what does the equation change to in that case? So you should be able to solve that out, I would hope. Is it P2 equal to P1 times C, P2 equal to P1 times the natural log of S circle of T2 minus S circle of T1 minus C over R, P2 equal to P1 e to the S circle of T2 minus S circle of T1 minus C over R? Or is it P2 equal to P1 e to the C over R? Okay, and I'm going to erase this for a second here because I wanted to then also cover the various cases or to cover the case where the constant's specific heat as well. Oh boy, isentropic. So typically if we have a constant specific heat, we'll typically we're given K. But we could be given CV or CP. And if we're given K, recall that CP is equal to K times R over K minus 1, so you would need to get that gas constant, and CV is equal to R over K minus 1. Okay. But if we have a constant specific heat ideal gas that's isentropic, that's a mouthful, then the equations become this. 0 equal to, you have two options. Either the one with constant pressure, which looks like this, because that integral, remember this S circle up here that we were dealing with was approximating an integral. This becomes the log of T2 divided by T1 minus R times the natural log of P2 over P1, right? So this just approximates S circle of T1 minus S circle of T2, or the CV version plus R times the natural log of V2 over V1. Okay, so this is isentropic ideal gas. isentropic ideal gas with constant Cp/Cv. Okay, so if we have that scenario, then we can write it this way, and you can work out. You can actually work out using the fact that I'm not going to go through the whole derivation because I don't think it's that important. It's not actually too hard to do this derivation, so if you want to see me, I'll show you. But using the fact that for an ideal gas, PV equal to RT, we can actually find that T2 over T1 is equal to P2 over P1. This one is pretty straightforward, the K1 minus 1 over K1 to derive. This one is a little more challenging. V1 over V2, not substantially, so about equal, I guess, these two. But this one is a bit more challenging to prove if you want, and as I said, you can come see me if you want to see how it comes out. But these three relations pop out of these two equations that I have up here, and the fact that PV equal to RT. Okay, so you can they come from up here, and PV RT equal to RT. Okay, so you can use these relationships to help you find, say, the new temperature, the new pressure, new volume, what have you, by following through here. It's simple algebra, but it might be multiple steps, and depending on the case you're trying to derive. Okay, so an interesting thing that happens is, let's look at the PV and the I'm going to erase this now. Look at the PV and the TS diagrams here, is that we can find that on the PV diagram, if n is equal to 0, we have a straight line here, n equal to plus or minus infinity, we have something like this. What am I talking about? Polytropic processes. The reason that I'm talking, I should have mentioned this first, but the reason that I'm talking about this is we can actually relate n and k from this one. So remember, a polytropic process says P v to the n is equal to a constant, which means obviously P1 v1 to the n is equal to P2 v2 to the n, which means that P1 over P2 is equal to v2 to the n over v1 to the n, or v2 over v1 to the n. And if I wanted to flip that relationship, then P2 over P1 is equal to V1 over V2 to the n. Okay, so now you can kind of see that this polytropic process is very similar to the process we have written up here, right? Okay, so the interesting case is going to be when we have, remember this is isentropic ideal gas. So then we can look at the various scenarios. We have that n equal to -1 here. This one kind of looks like this. N equal to 1, which is where the temperature T is constant. And then finally for n equal to K, which is S is constant. Right? The entropy is constant. It's isentropic in that case. So when the n is equal to K, we have an isentropic polytropic process, right? That's an interesting kind of scenario that we can run across, where n is equal to K implies that we have an isentropic process for an ideal gas. Which is a really neat thing that you can see in this case, on the PV diagram. Your book also shows the TS diagram, so if you're interested, you can take a peek there. Okay, and then your book goes through a bunch of examples, again using making assumptions. I'm not going to go through all of them. I'll just do, say, the turbine to work through it a bit, but it goes through a bunch of the other ones, and I'll just give you the end results of those ones. But you can find the isentropic efficiencies as well. So the turbine. This one works out. This one works out to be something like this. We know that WCV dot over M dot is equal to H1 minus H2, right? Where one for a single inlet, single exit. Assuming no heat transfer, which is a common assumption in the turbine, but it can't always be assumed that way. So I'm assuming H1 is the inlet, H2 is the exit, right? And this is going to be at steady state. We know that the work works out to be this, because we can commonly also ignore the kinetic energy terms and the potential energy terms. So it just reduces to this, right? That's the amount of work that I have done. If we're assuming that there's no heat transfer, which we assumed up here, then we can come down here and we can say, okay, well, if it's isentropic, then we should find that S2 minus S1 has to be equal to 0 if it's isentropic. Okay, so if it's isentropic, then this has to be the case, right? So that means 0 equal to, well, the heat term went away, that sum over of q dot over h dot or whatever, so that would have to be equal to sigma dot over m dot, say m1 dot. But the problem, of course, there is that the only way that that can be is either the mass flow rate goes to infinity or that sigma dot is equal to 0. So basically, if we were isentropic, then this has to be reversible. But we know real processes are generally not reversible. So this is how we're going to get to an efficiency, right? So not internally reversible. Oops, reversible. So that means S1 with no heat transfer again. S2 minus S1 is going to be equal to, for the real process, that's going to be equal to sigma dot over m dot, right? And that's going to have to be greater than 0, because sigma itself has to be greater than 0. Well, sigma dot over m dot has to be greater than 0 in this case, in order for if it's not, and if there are any kind of irreversibilities. Okay. Now this part is kind of hard to see without to understand without drawing a diagram. So I'm gonna actually draw the diagram. Your book does a good job of this, but I'm gonna actually draw the diagram so that we can kind of understand what's going on now when I'm trying to get the efficiencies. And then, as I said, I won't derive other ones. I'll just give you the end result. But in this case, imagine I have my molar diagram, my HS diagram, and I have some process, and this is a constant pressure line. This is an isobar, P2. That's my second pressure here. Okay, so what I'm going to do then is I'm going to have the state, let's call this state 1, and I'll call this state 2. Okay, that's state 1 and state 2. And then I'm going to have another state, which I'm going to call we'll call it S2. Your book likes to call it S2, so I'll call it, or sorry, your book likes to call it 2S, excuse me. So I'll use the book's notation here. So in this case, this is the this is, if I went from state 1 to state 2, this is at pressure, right? Pressure, oops. Pressure 1. At pressure 1, it goes something like that. So the actual path that this process takes goes from 1 to 2, but I could imagine a case where I had done this isentropically, right? Which is this state right here. If I go straight up and down, I know my drawing is not great, but if I go vertically straight up and down, back down to that pressure, then this is my 2S state. This is my isentropic I'm going to call it the isentropic version of the second state. Okay, so this is my isentropic version of the second state. And this is the one that's marked in black is the true second state. Okay, so that's the actual second state that we had. So the idea is that if I had stayed at constant entropy, 2s is what I would have found. So I could if I was going to the tables, I would take my value at S1, and that would be the entropy that I use for the isentropic value at 2s. Right, and that pressure P2. So you'll obviously, if you know P2, you'll be able to find 2s just fine because you already know S1, and then you'll also know P2. So you'll know S1, P2, and S2 has to be in this isentropic version of the second state has to be the same as S1, right? So this value, notice that I'm going up and down H here. So that means that H isentropic H1 minus H2s would be my difference between those two states. And then my non-isentropic version would be H1 minus H2. So this is my real world process. Okay, so that means that my isentropic version then, so remember up here, we were assuming no heat transfer. You have to keep all of those steps in mind, but assuming no heat transfer and all of that good stuff, that means that over here I had my W dot over M1 dot was equal to H1 minus H2. So that's my W dot there. And then this is going to be my W dot over M1 dot at S, which is that isentropic. When I put this S here, I'm meaning isentropic is going to be equal to H1 minus HS2. Or 2S, sorry. H2S. That's how your book writes it. Okay, so this is going to be my isentropic as so if I had done it in a internally reversible manner, this is what would have happened, and this is what actually happened. Right now, I'm not saying that I can't have isentropic, then or that I can't have internally reversible, because if I have a situation where it's internally reversible, then obviously I would reach an efficiency of 100%. So that means that my eta T, which is not possible in the real world as we know, but my isentropic efficiency then for a turbine with no heat transfer, right? With no heat transfer, whatnot, is going to be this divided by this, W dot over M dot S. And obviously, since this is true with no heat transfer, this becomes H1 minus H2. So that's the actual enthalpy values divided by H1 minus H2S, which is the one assuming that I was isentropic. Okay? There we go. We're going to get very similar things for other things. So this is the turbine, ignoring heat transfer and KE and PE effects. Then we'll have the nozzle, which gives me eta nozzle, which is equal to V2 squared over 2 over V2 squared over 2 at the S state. Okay, so it's a similar idea. Assuming that it had been isentropic, what is my velocity? Which you would have to work through the details to figure out, of course, in the problem. How about compressor and pumps? What I find is A to C slash P is equal to H of 2S. Again, that's my isentropic, assuming that it had been isentropic, over H2 minus H1. That's my efficiency there. And obviously I'm making certain assumptions about kinetic energy terms and things just like above. So that's what you would find in those cases. Okay, the very last topic. Sorry this video is running long. I misjudged the time. I'll try to do a better job in the future. But the last topic is heat transfer and work. An internally reversible steady state flow, processes. So if it's internally reversible, assume single heat transfer internally reversible, steady state. If I assume all of those things, if it's internally reversible, and there's only a single heat transfer, Q dot over T, which is that T, by the way, is the temperature at which the heat flow is happening. It's going to be zero is going to be equal to this plus m dot S1 minus S2. M1 dot, we'll call it. Could be M2 dot, right? This is a single inlet and single exit as well, the formulation here. But it's equal to this because that sigma term, if it's internally reversible, is 0. Remember, sigma is the strength of the internal irreversibilities. So if it's 0, then the strength is obviously 0. If there's no strength to the irreversibilities, that means it's reversible, internally reversible. So what does that mean? Well, that implies that Q dot over M dot is going to be equal to the temperature at which all of this stuff is happening times S2 minus S1. So this should kind of remind you of the, in fact, it should remind you of the TDS equations, right? So, which is exactly what we were seeing before. Right? Something like this. And I believe we've already discussed, but on the TS diagram, you can then, of course, figure out how much heat transfer has happened by simply looking at the area under the curve. Okay, so this is an isentropic, right? This is an internally reversible, sorry, not isentropic, it's internally reversible process. And then work, we can do similar tricks. We know that the energy balance equation, I'm not going to call it CV here. I am going to assume still, again, single inlet, single exit for simplicity, but obviously there could be certain circumstances where that's not true, so you have to be careful in those cases. Z1 minus Z2. Because obviously then you would have multiple terms that get added and subtracted here, so you have to be careful there, but we'll just make the assumption of single inlet, single exit, because that's what most of the problems are going to look like. Well, if it's internally reversible, again, we're going to have a case where this is true, right? Because internally reversible means that sigma term went away, so this must be true for the Q. So that means that W dot over M dot and 1 dot in the internally reversible case is equal to, well, it's that integral 1 to 2 of TdS plus H1 minus H2 plus V1 squared minus V2 squared over 2 plus G Z1 minus Z2, right? Because we just replaced this with our expression up here, which again assumed that it was internally reversible. And then if you recall, we had some TdS equations, so we can play around. We can do a lot of playing around with the TdS equations, like the TdS equal to dH minus V dP, for instance, which means that, and this is a lowercase s, since these are lowercase h and p, or lowercase h, I mean, and v, lowercase, that 1 to 2 of T ds is equal to H2 minus H1 minus the integral from 1 to 2 of V dP, which means if I substitute that in here, this thing up here can be substituted in here. Obviously, if I subtract the H2 and the H1 over, I get H1 minus H2. So if I do that, then I can rewrite this as W dot over M dot and 1 dot internally reversible. Again, this all is assuming internal reversibility, so don't forget that part. But that's going to be equal to, well, I can rewrite this whole thing, and what I'm going to find is that is equal to minus integral from 1 to 2 of V dP plus V1 squared minus V2 squared over 2 plus G of Z1 minus Z2. Okay, so we can play all of these kinds of games with the work. Obviously, if the kinetic energy and the potential energy are negligible, you just get a very simplest expression here. So we can play those games. And the final topic is in polytropic processes. What we find is that we find that in that case, then W dot over M1 dot, in the internally reversible case, remember we're assuming single inlet, single exit, so you have to adjust these equations accordingly. Integral from 1 to 2 of V dP, well, that has to be equal to some negative constant. I'll call it C. I'll let C be my constant here. Or maybe capital K. Capital K. To the 1 over n. Integral from 1 to 2 of dP. Oh, oops, dP. Over P to the 1 over n. Because this is a polytropic process, remember P V to the n is equal to a constant, which implies that V to the n is equal to that constant, we'll call it capital K, over P. And then obviously you can substitute into, you should be able to carry this out further, but that means this implies that equation up here implies that W dot over M1 dot of an internally reversible process that's polytropic is equal to minus n over n minus 1 P2 V2 minus P1 V1. So they just perform the integral for you for n not equal to 1. And I'll let you figure out the n equal to 1 case. You should be able to figure it out if you can do this integral, if you can do this integration. So finally, using some of those equations that we found above, remember way up here we discussed equations like this, these equations. So we can use those down here, assuming it's ideal gas. Again, we're making a lot of assumptions. Single inlet, single exit, ideal gas, internally reversible, a lot of stuff that's being assumed here, but it'll be useful in those cases when we know those cases. So you'll have to remember how to identify when is it an ideal gas and whatnot. Then that's going to be equal to minus nr over n minus 1 of T2 minus T1 for n not equal to 1. I'm just playing around with those relationships up there, so that I just highlighted, I circled up there, way up there. Minus nr T1 over n minus 1 of P2 over P1 n minus 1 over n minus 1, n not equal to 1. Or finally, let's do one with n equal to 1. That's going to be equal to minus r times t times the natural log of P2 over P1. Okay? So basically just playing around with the ideal gas case, remember PV equal to RT, and these relationships that I had up here become useful for some of these transformations, those ones that I had for some of those transformations. But if you use those, these are the equations that you come up with. Okay? So single inlet, single exit, internally reversible, ideal gas. These are the equations that you can come up with for work. And we're also, of course, assuming steady state and internally reversible, right? All of those things. That's all that I have for this video. Hope to see you again soon.